My name is Ettore Barbieri and I'm a senior researcher at the Japan Agency for Marine Earth Science and Technology, or JAMSTEC, and this is the Yokohama campus. JAMSTEC is a national research institute and has recently celebrated its 51st anniversary. JAMSTEC is one of the top marine research institutes in Japan and has 6 research vessels, one huge deep-sea drilling ship named GQ, several autonomous underwater vehicles, and a submersible named Shinkai 6500. I am one of around 300 researchers working on global environmental changes, sustainable marine resources, geodynamics, and large-scale scientific computing, including atmospheric and earthquake computer simulations. I am a computational scientist, someone in between computer science, applied mathematics, and engineering. My forte is solving equations where things change suddenly and rapidly. This field initially gained popularity in engineering, where components and materials can break, a topic known as fracture mechanics. But fractures arise in many areas, from biology, network science, and quantum mechanics, to mention a few areas where I've been involved. I'm blessed to collaborate with colleagues from diverse backgrounds. I'm particularly grateful to one of these colleagues who introduced me to biomechanics. Understanding fractures can help reverse engineer nature. After all, there is no patent infringement on what nature does. Examples of our collaborative research on biomimicry include the impact resistance of the mantis shrimp, a species with really powerful clubs. We also worked on the toughness of antler bone, where counterintuitively loose bones can increase energy absorption during crashes. Another fascinating creature we studied is the sea cucumber, which can change its skin stiffness according to the surrounding chemical environments. It can go incredibly soft or incredibly stiff. If we understand these mechanisms, we can design more resistant armor, or we can design shape-shifting robots that can go where humans cannot. In earth science, fractures appear in earthquakes. Although I'm not directly working on earthquakes, many colleagues here at JAMSTEC study the effects of earthquakes. An emerging trend in earth sciences is the digital twinning of the oceans. It is a technology that creates a virtual copy of the oceans based on data from the real world and computer simulations. My contribution is reconstructing food webs from species data using network analysis. These computer simulations are enormous and require supercomputers. JAMSTEC has one called the Earth Simulator, which is housed in this hangar. This is Earth Simulator 4, the 4th generation of a series of supercomputers that started in 2002, when it was the fastest supercomputer in the world. It currently has a speed of 19.5 petaflops. 1 petaflop is 1 quadrillion operations per second, and it's the 39th fastest supercomputer in the world. It is used for global warming projections. The results are included in reports for the Intergovernmental Panel on Climate Change. The next challenge I plan to tackle soon is related to the fracture of sea ice. The thinning and breaking of sea ice in the Arctic is a significant issue caused by climate change. JAMSTEC is building a new icebreaker ship to travel the farthest possible distance in the Arctic. If we can reproduce in the computer how ice fractures, we can then come up with the best design of the ship hull for the icebreaker. Same simulations can help understand the causes and the consequences of climate change on creating icebergs in the Arctic.